Hey everybody, this is going to be the second set of slides for Module 4. So we're going to talk about interpreting coefficients. I have a different video about interpreting coefficients just from a regular OLS model, but this is going to be more of interpreting the coefficients using logs. So interpreting them when we transform one of the variables from um, like a regular count variable or regular continuous variable. When we take the log of something, we'll be able to interpret it as percentages or elasticities if that rings a bell. The first thing we're going to do is we're going to have our regression model y equals beta 0 plus beta 1 x1 plus beta 2 x2 and so on. So from our data, we can estimate a regression function that looks like y hat equals beta 0 hat. So that's our estimate of beta 0 plus beta 1 hat, which is our estimate of beta 1, and so on. So the way we would interpret each of these things is beta 1 hat is going to be the impact of x1 on y. So if I increase x by 1 unit, whatever unit that is measured in, so for example, if it's measured in dollars, if I increase my x by $1, if it's measured in hundreds of dollars, if I increase my x by $100, if it's the number of square feet in a house, if I increase the square footage of my house by 1. So it's always going to be a 1 unit increase, and it's going to be that effect on y. So if I increase my square footage by 1, then y is going to change by beta 1. Beta 1 could be 5. Maybe I increase my square footage by 1, and then y is going to change by beta 1, which is 5. Or it could be less than 1. It could be a whole bunch of different values. It could even be negative. But this is only after holding everything else constant. So for example, if this is just square footage and this is number of bathrooms, number of bedrooms, maybe what school district you're in, what police department your house is a part of, all things like this. So holding those things constant, the only thing I'm going to change is the square footage of your house, and that's going to be the impact of beta 1. So when we say we expect, we're talking about an average. So when we expect an increase of beta $1 given a 1 unit increase in square footage, that means that on average. Now, of course, this is not always going to be true. In some cases, we can have more. In some cases, it can be less. But on average, we're going to expect this one, with a 1 unit increase, we'll have a beta 1 increase in whatever y is measured in. So you may see beta j simply described as the marginal effect of regressor xj in many studies. That's because the researcher is pretty much going to assume that you understand what a regression is kind of implying and what the interpretation would be. So we can try a little bit of different interpretations with slightly different modifications of the variables, specifically taking the log. So this table is super important. You should come back to this all the time, often, because sometimes you might think, because the first thing we do is we do this level where we have y and x, where we have a change in y equals beta 1 times the change in x. So if x changes by 1 unit, y is going to change by beta 1. But this is fine. But if we wanted to do something more like with percentages, like for example, housing prices are oftentimes logged. That's because we want to say a 1 unit increase in square footage increases the price of the house by some percent, by beta 1%. So for example, that's this log level. So if the dependent variable is logged and x is normal, you say a 1 unit increase in x causes a beta 1 times 100% change in y. So now y you can think of as percentages. Whereas if we do it the other way around, where y is regular, so y is just the house price, but we log x, the units of x now become percentages. So a 1 percentage increase in square footage leads to a beta $1 amount change in y. And then similarly, if you have log log, it would be a 1% change in X equals a beta 1% change in Y. So this would estimate an elasticity. If you're familiar with elasticities from economics classes, then this is kind of how economists typically estimate these things. So elasticities are important pretty much when they're above 1 or below 1 or pretty much exactly equal to 1. And that's what you should kind of be thinking about for those betas. So here's an example of a pharmaceutical market. Some regression was ran, and we have the firm revenue, call rev, and we have advertisement expenditure, advertisements, and the number of years the firm has existed, which is we're going to call it years. So rev and advertisements are both going to be measured in millions of dollars. So first we're going to run the regression just level. So just Y and X, just totally normal. So what this is going to say, this regression here, what this is going to say is that if first we're going to interpret this 65. To interpret 65, we have to set this equal to 0 and this equal to 0. So for example, if I spend $0 on advertising and I am in existence for 0 years, my revenue is expected to be about $65 million. Now this is pretty uninterpretable because if you're not in existence at all and you spend no money on advertising, you shouldn't expect to make money. But maybe these advertising dollars and these years in existence variables the averages are much higher, and we're talking about data up in that stratosphere rather than the very low values. So for example, if we try to interpret this next coefficient, meaning that if we increase the number of dollars spent on advertising, because they're both measured in millions, if I increase my advertising budget by $1 million, revenue will increase by 2 times 1 million, so 2 million. If I increase my advertisement by 4 million, it would be 4 million times 2, which is going to give us $8 million, right? So there's seemingly a doubling of whatever dollar I spend on advertising, it's going to give me double in revenue. But this is only controlling for how many years I've been in existence. So this question here is, do you think this marginal effect can be true for all values of advertising? Probably not, right? So probably it's the case that once you're spending millions and millions and who knows, even, suppose in a crazy world, billions of dollars on advertising, that $1 extra or that $1 extra $1 million is probably not going to give you all that much of a return. If you're increasing your advertising budget from $1 million to $2 million, that's doubling. But if you're increasing your advertising budget from 40 million to 41 million, that extra benefit is not going to be as significant, right? So if that's the case, and you can make that claim, then you're saying that that 1 unit increase is not a constant effect across the entire distribution, meaning that going from 1 to 2 is not equivalent from going from 40 to 41. If that's the case, then you have to kind of consider this, right? We have to think, well, maybe if that's not the case, then maybe we need to change the functional form of our independent variable. So for example, in this equation, we can take the log and then the log of both sides. So for now, we're saying if I increase my advertisement, the percent of my advertisement by 1, if I increase advertisements by 1, then the log of my revenue, so the percent increase is going to be 4%. So if I increase my advertisement by 1, then my revenue is going to increase by 4%. So 1% equals 4%. And then if I increase by 2%, it's going to increase by 8%, right? So it's just a linear relationship like that. So now this one is going to be the expected revenue is going to be a function of the percent increases of my advertisement. So for example, if I increase my advertisement by 1%, my revenue is going to increase by $0.4 million. So that's going to be about $400,000. And this is just how you would interpret this, right? This is going to be these units now get transformed into percentages, and these units get transformed into don't get transformed rather, and are just regular dollar amounts. So a 1% increase in advertisements leads to a $400,000 increase in revenue. And then in this one, finally, we have the log of revenue, which means that this is now in percentages, and this is in just regular dollars. So a $1 million increase in advertisements leads to a 2% increase in firm revenue. So these are just different ways of interpreting the coefficients based on how you want to specify the model. And you have to do a little bit of thinking or theoretical research, maybe some plotting, to kind of deduce which functional form you should be using. But at the end of the day, whatever you pick, you should always be revisiting this table, this reference table, and looking at the different relationships and the interpretations. Okay, so sometimes we include variables that are expressed as percentages in our regression. So to interpret them, we need to know the difference between a percent change and a percentage point change. So if a variable x changes by delta x, its percent change is delta x over x times 100. So if I have 10 bedrooms in my mansion, and the change is 1, if I add in 1 bedroom, it's going to be 1 over 10 times 100. That's going to be a 10% increase in the number of bedrooms. So here's an example about investing into the stock market. So a percentage point is just rather simply a unit of 1%. So for example, if I have 40% of my wealth is in stocks, then I say I want a 1% percentage point increase. That would go from 40 to 41. Whereas a 1% increase, rather than a 1 percentage point increase, would be 1 divided by 40 times 100. And whatever that happens to be mathematically would be the percent increase. So here's some more information on this. You can keep reading at your own pace. Finally, the last thing I wanted to talk about was I mentioned that when you have multiple regressors, you can do stuff like quadratic terms or even cubic terms, right? But this really complicates the derivative or the interpretation of the coefficients. So for example, if you do use a quadratic function, right, something like that looks like this, then the derivative or the interpretation, if I increase my 1 unit increase in square footage, then that would be beta 1, which is what we normally interpret. But now I also have this guy here. So it'd be 2 times beta 2 times the square footage of it already. So it can get complicated. And then further, there's something called an interaction term, which we can talk about if on a case-by-case basis if people are interested. But effectively what it is you have 2 variables by themselves. You can think of this as maybe years of education, and maybe this is gender, right? So maybe you think, and this is like wages, right? So forget this last piece, but maybe it's the case that you want to try to measure some sort of gender gap, right? So education is your control variable, and you want to see if this is significant. So if men happen to make more money than women for the same exact job, controlling for education, then you'd want to know that. But it could also be the case that maybe education, the way education enters the model, is different for men versus women. And that's what this would do. Now, it's a little bit more complicated than just what I'm saying, because this derivative is going to slightly change when we take the derivative with respect to education, which would be x1. So it's going to be different depending on what x2 is. So the derivative change for women would just be beta 1, but the rate of change for men is going to be beta 1 plus beta 3. So it's a little bit nuanced, but it's a really handy tool if this is something that if you want to compare 2 groups, something like that. So this is all I have for this coefficient interpretation given alternate specifications. So rather than just the simple OLS interpretation, this is a little bit more nuanced, a little bit more stuff here. For your projects, this is something that you might want to think about, whether it's logging variables or whether it's comparing 2 groups with an interaction term, or maybe allowing for a nonlinear effect via a quadratic function. These are all things that you might want to think about.